Good morning, everyone, and welcome to this. It's the 16th ETP4HPC webinar. I am Pascal. I'm the communication manager for ETP4HPC, and my colleague Mike is also here to help run the show. For those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in high-performance computing, or HPC. And we are a private member of the Euro-HPC-JU, which is the organization in the European Commission that addresses HPC, to put it simply. And our role is to propose research priorities for Europe in the area of HPC. Before we really start, I have a couple of practical information for you. So this webinar is recorded. You will receive the link to the recording on Monday. This webinar is in listen-only mode, but you can use the GoToWebinar control panel that's illustrated here to ask questions or download handouts. So today we have two handouts, the slides of the webinar and the white paper we're going to talk about. And concerning questions, well, you can submit questions at any time during the presentation. We will share them in the chat so everybody can see them, but we will handle them at the end of today's session during the Q&A. So now let's get to today's topic. So today we have invited two of the authors of a white paper published by ETP4HPC that's entitled Task-Based Performance Portability in HPC. ETP4HPC has published 6 such white papers until now. We're doing this while we are preparing the next edition of our Strategic Research Agenda, the SRA. And all of the white papers will be integrated in the SRA eventually. So all of these white papers can be found on our website, and today's is available as a handout, so you can download it right now within this webinar. The agenda. Well, here are our speakers today. We're very happy to have Olivier Homage and Paul Carpenter. Welcome to you both. Thank you for being here. Olivier Homage is a full-time researcher at INRIA in Bordeaux since 2003. His main research topics include parallel runtime systems, programming models and languages for high-performance computing applications. And Paul Carpenter is a senior researcher at the Barcelona Supercomputing Center since 2011. And his research interests include performance portable parallel programming models, system software, and energy efficient architectures. So they will each focus today on a specific European initiative, actually, StarPU and OMPS respectively. And so after their presentations, we'll have the question and answer session moderated by Mike, and we are looking forward to your questions. So this will take us to noon. We'll do our best to finish on time. So now is the time to hand over to our speaker, Olivier. Are you ready?
Yeah.
Okay, so I will hand over to you. Yeah, you should be able to share your presentation now. Yes.
Yeah. Okay.
Yeah, we can see it.
Thank you. So good morning and thank you for joining this webinar. So I'm Olivier Homage from INRIA in Bordeaux, and I'm going to present some of the findings that we developed in the white paper that Pascal presented together with Paul Carpenter and Siegfried Bender. And I will use the StarPU runtime system as an example to expose the ideas that we developed in the paper. The key insight that I want to introduce today is first that porting applications is difficult in HPC and must be successful in a very short time. So every time a new supercomputer becomes ready in production, applications have to run efficiently in a very short time to take advantage of the new hardware. For that, we think that application should be expressed in a way that facilitates the effort of performance portability. And we think that one of the means to achieve that is to rely on task-based programming models to express application and workflow in that performance portable way. So this is what I'm going to present now. So the reason why application porting is difficult and must be successful in a short time is that the lifetime of supercomputer is very short. It's between 5 to 10 years, depending on the hardware. And in the meantime, complexity of hardware is increasing, the heterogeneity is increasing, and also the reason for these increases are the increasing diversity in the proposed and designs of machines. We can see that, for instance, in the various rankings, where these are not the same machines that are at the top of this ranking. And even if we look at the top 500, the top machine of this top 500 are all using a different architecture. So if you port one application on one machine, you have to do the effort again on another machine. So what we want to convince you about today is the idea to program application readily for performance portability, especially by focusing on expressing what is the work to be done instead of managing workers and resources explicitly. So the idea to rely on abstractions instead of hardware-dependent work divisions. We can see an example here. If we express the work in terms of workers directly, and then if there is some load imbalance, the burden of managing the load imbalance and rebalancing the work is on the application programmer, and that's not convenient. So what we promote is the idea to express instead the work to be done and rely on third-party runtime systems to do the work of choosing which resource to use for each task. And a second aspect of that is really to confine the effort of adapting applications to new hardware inside selected key routines, which we call tasks, and to avoid having to rewrite the whole application every time. So in the ideal manner, every time you have to port an application on new architecture, you would have to tune only some selected kernels to adapt the application on a new machine. And the goal of these ideas is twofold: is to make it easier for humans programmer to develop application on HPC platforms, and also to make it easier and safer and more effective for tools, so that tools can work on behalf of the application programmer. This is the real key thing here. So one way to do that is the idea that we define what task-based parallel programming. So the idea of task-based programming is twofold. First, to separate the development work into multiple concerns. So one about keeping the general application algorithmics. So this is the algorithmics that is dependent on what the application is trying to express. So that can be a simulation for weather forecast or things like that. Separate the concern of low-level optimization, so inside task kernels, and also the work of managing resources and the work assignment, which is the work of the runtime systems. And the purpose of that is to maximize the long-term investment in software development. So what we want is to keep the application structure mostly fixed and mostly stable on the long term, and only have to change specific routines when porting on a new platform. So the idea of task-based programming is not new. The core of the model is considered mature right now. It was introduced in the mid-90s and has been standardized in OpenMP in 2008. And there is also an active research ecosystem to extend and develop the model. I've listed here some examples of initiatives that are ongoing, and also identify some that occurs in Europe. And as I said, I will use StarPU as an example on what we can do with task-based programming and how it can help with HPC application development. So the StarPU runtime systems was introduced in 2009 in Bordeaux, and it was from the start designed to drive application on the kind of nodes that you see on the right. So heterogeneous nodes where you have CPUs and specialized accelerators. And the idea was to use all the resources and give access to all these resources to the application. And StarPU can be used either directly as a C or C++ or Fortran library, or through compilers, OpenMP for instance, and also it can be used through parallel numerical libraries. So you can call a routine that is parallelized with StarPU, and all the parallelization work is hidden in that routine. The programming model at its core is very simple. So it's the idea to have some kernels that are annotated. So these kernels are just functions, which we call tasks, and which express the potential parallelism, and some dependencies information, so which are the annotation that we put on the function, that gives the degrees of freedom in realizing this potential parallelism. And this is these degrees of freedom that will be used by runtime systems to do the optimizing work. In order to capture these constraints, the tasks are submitted by the application in a sequential manner to the application. So we see here that we submit to StarPU a new task. We do some kernel. So this is a priority ref here, or whatever. Then there is another kernel and another task that is submitted, and we see that this second task uses the result of the previous task. So there is a dependence edge that is recorded in StarPU between these two tasks, and so on. We build a word graph of dependencies which capture all the constraints that have to be enforced. And as long as the runtime system respects these constraints, we guarantee that the result of the execution will be valid. And we use this information and the freedom for optimizing to let StarPU do the decision of mapping works on resources on behalf of the programmer. So in order to do that, StarPU uses a cooperation between three engines. We have the scheduling engine, which implements some scheduling policies. We can be either anticipative, so StarPU can plan in advance on which resources to put some tasks, and can also be reactive. So after the fact, it can also rebalance the work if some node becomes idle earlier than expected. It can still work from the neighbors. So the two aspects can work together. The second engine is the distributed shared memory engine, which is in charge of managing the data transfers between all the memory space. So the memory space on the main machine, the main memory, the memory space on the GPU boards or accelerator boards, and also manage all the data replication and data consistency. And there is also an engine in charge of modeling the performance of tasks, which helps in deciding which unit to use for a given task. So an example of using this performance modeling to do the scheduling, so the mapping of the task on the resources is on this slide. We see that there is a new task that is submitted here, and StarpU has to decide on which unit it should be executed. So for that, it will use the performance modeling engine to infer what would be the cost of this task on any of the resources that are available. And for that, we see what we have already planned. And we see that here we have a red task, a blue task, and a light blue task. So this is what is already planned. And if that task was executed on this first core, it would finish at this point here. And the heuristic that we use is that StarpU picks the units where the task would finish earliest here. And so it would put the task on this first GPU here. So it uses an history-based learning to learn about the cost of the task for different devices, different variants of the routine, and given the input size of the data given to the task. We can also go further once we have tasks, and instead of just considering variants of routines, we can also consider variants of either one routine or a whole subgraph of tasks to perform a computation. So this enables adapting the parallelism to different devices or different contexts where you can have, for instance, a GPU which is very powerful, so needs a lot of work, and a CPU which has cores that are much less powerful, so where you need a larger number of smaller tasks to have an even balance. So this enables to adapt the graph of tasks during the execution of the application. There is also a next step to that, to manage task graphs that are submitted by distinct applications or modules within an application. So if you have an application which is parallelized with StarpU, which uses a library which is also parallelized with StarpU, StarpU can drive these two graph of tasks within a single instance and control the resources assigned to each of the two graphs. So we can see that we have one graph which is in blue here. So we have these resources assigned to the blue graph here, and then as the execution evolves, we can resize the set of resources assigned to this graph, and likewise for the yellow one. So this enables composition of multiple codes that are parallelized with StarpU within a single application. There is also the option to do that with different runtime systems. So we cooperated with work colleagues from BSc on having StarpU and OMS work together, and we can, for instance, offload one task as a whole parallel computation scheduled by OMS. So here we see that StarpU assigned two of the cores to this parallel task, and OMS will schedule this subgraph on these two cores here. So this was a version of offloading the work from StarpU to OMS, and we can also have the situation where we have two runtime systems that work side by side because they are used in distinct libraries, for instance. So we can also have StarpU and OMS that work side by side within the same application. And for that, within that intertwined project, we also did work on defining APIs that enables these true runtimes to negotiate the access of resources. So we can see here on the example that we have homes here that start with 2 cores and CPU with 2 other cores. And as the computation evolves and the need evolves, we can have homes that uses all the cores for some time for some heavy computation, and then relinquish some of the resources and CPU use them to do some other computation. So this true runtime system can negotiate access to resources during the application. All that I presented so far was within a single node, but there is also the issue of managing a whole distributed computation. So StarPU supports 2 models for that. So either a master worker model where we have a master node that drives a set of worker nodes. So this is the simplest one, but there is a risk that the master can become a bottleneck if the session is very large. So we also have what we call the fully distributed execution model. And in that model, there is no master node. So all the participating StarPU instance get a view of the task graph, and they pick only a subset of the task that they execute themselves. So the selection of who execute which task is based on the data ownership. So a node will execute a task if it owns the data where the task is writing to. And we can also use the task graph to provide some services such as failure tolerance. So the way that we implemented it is that we do replication on neighbor nodes in distributed computing. So if we have a situation where we have 3 nodes here and node 1 for some reason fails, the node 2 can become the backup of the node 1 and supply the result of some computation that was computed on node 1. So the interest of that is that we take advantage of the knowledge of the task graph to only back up what is really needed and to quickly start again at the right point when there is a failure. So as a wrap-up for the StarPU runtime system, so it chooses the task graph to provide a comprehensive resource management. So for all the kinds of processing units that you may have in a node, so CPU, GPU, FPGA also. It chooses the task graph to both plan scheduling and also rebalance scheduling to work stealing. It chooses performance modeling to choose among heterogeneous resources. There is similar support for memory management that I did not discuss today, and using the task model, it is able to perform freely with the ecosystem in terms of interoperability, composability, and malleability. And to conclude on this presentation, on a white paper, what we want to promote today is the idea that application should be made more programmer-friendly and tools-friendly in terms of platform independence, malleability, asynchronism. For that, it needs to use stable interface between all the components, so the main application algorithm, the library, the kernels, and the platform-tuned software. For that, we think that the task abstraction is the right way to go. And more generally, what we think is that we need a greater degree of trust from application. So in the same way that structured programming was introduced some decades ago to make life easier both for programmers and compilers instead of working on assembly language, we think that we are at the same turning point here, where we need an application that can be processed by tools to do the optimization work on behalf of the programmer. So thank you.
Thank you, Olivier. So Paul, are you ready to share your presentation? Good.
Sorry, I think I was on mute. Do you see the screen now?
Yes, we can see the screen and we can hear you now.
Okay, thank you, Pascal, and thanks, Olivier, and good morning to everyone. So I will complement Olivier's presentation with some perspective from the work on OMPs being done at BSc. So application development used to be, I guess you could say, it used to be easy in that there was a reasonable correspondence between what was written and your kind of mental model or the execution model maybe of C and what is actually happening at the system. And over time, this has stopped being the truth, right? So with multi-cores, it started to get difficult, and then heterogeneous compute architectures, deeper or heterogeneous memory hierarchies, even the deeper software stack, for instance, behavior of MPI and so on, may be a little bit tricky to understand. And that meant that what maybe was a sort of clean interface became leaky, and it was necessary to know internals or lower level details in order to get performance. And the risk of this is that the application becomes very complicated. It becomes maybe dependent for the machine or full of if-defs. The structure maybe becomes refactored depending on the architecture that you're targeting. And in the same way as Olivia said that this is not a good thing, we agree with basically the same point, that putting all this knowledge into the application code is not a good idea. Not just from the portability, but also it means that the application code becomes sensitive to latencies. Things like the send receives and the fork join model are inherently latency sensitive. So from our perspective, the job of the programming model is to provide a clean, stable interface to express the fundamentals of what you're trying to achieve. So then the machine or the lower level software, can do the execution in a way that matches the resources that you've got. So the application doesn't have things like OMP num threads and thread private. These things are very tempting, and I know how tempting they are, but it makes the application very rigid. And really, I think Olivia said the same thing about try to instantiate work in the application to be executed. And we see a task model in the same way as being an excellent, essentially the right model to express the work that needs to be done so that it becomes more sort of throughput based. And one thing that's very important to us from the BSc side is standardization. So HPC, we're talking about HPC. HPC applications have very long lifetime, and they grow kind of knowledge inside the code base over time. So if an application developer is thinking of adopting a programming model, they need to have confidence that there will be long-term support, there will be good performance across a wide range of systems, and we see standardization, let's be specific, OpenMP standardization as a way to achieve this. And related to this, I'll also mention things like malleability, again, comes into this idea of not being specific about the resources. And just one note on the performance analysis, given the complexity of these machines, it's sometimes an inspired guess is very, very good, but often what you think is the problem is not really the problem, and therefore the performance analysis is very important to understand what the fundamental issues are. So OMPS, I think OMPS was in the title. OMPS is part of what we call the star SS family. So star SS is kind of the broad idea of task-based program, inheriting the sequential semantics of the original program. And I think we're doing this in all our efforts. So we don't have, for instance, Olivier mentioned the fully distributed star PU model. I don't think we have anything like that in BSE because we push the, the sequential semantics. But then there are two broad efforts. There's OMPS, which is the OpenMP-like variant, and comps I'll talk about later is more for scripting and coarser granularity. And it happens to execute in parallel, again using automatic detection of dependencies. This is the Cholesky example, again, now in OMPS format using pragmas like OpenMP, and the single mechanism, so these in-outs, does two things, and it's important that this single mechanism is used for both of them rather than trying to separate them. And this is the understanding dependencies among the tasks, allowing you to instantiate work well in advance of the data actually being available, plus also saying specifically what data is used, which can be used for locality scheduling, for instance. So just a quick picture, I won't go in detail, showing basically starting over 20 years ago, I guess, at BSE with the early work. You can see it's a large research direction at BSE. I'm speaking about it now, but I'm just down in one little corner of this effort. I mentioned earlier that standardization is important, and our effort on OMPS at BSE runs kind of in parallel to OpenMP. And we try to propose some of the more successful or mature ideas that come out of the OMPS research into OpenMP, and we've been very successful. These are examples of all things that have been proposed out of work on OMPS. Many of them, the reference implementation, came from BSE, it was developed at BSE, and this was allowed quantification and measurement of the benefits of whatever has just been proposed. While we do that, we also have more sort of risky efforts going on to try more advanced and complex features. It's used in a lot of projects. I won't read them all out. So OMPS has been going some time. The second version of OMPS is OMPS 2, which has a new Nano 6 runtime system, similar source-to-source compilation. And a few of the features I'll talk about in detail in a moment: the advanced dependency system, integration or hybrid OMPS plus MPI, heterogeneous hardware, and distributed systems. So regarding the advanced dependency system, part of it is defining what you're going to do, what kind of access it is. So in, out, concurrent, commutative, also multi-dependencies I'll mention in a moment. They're all now in OpenMP. Then there's defining what regions of memory are being touched. And we do support non-contiguous memory regions and partially overlapping ones. This, of course, has a trade-off in terms of the overhead. So it has slightly higher overhead, of course, than the simple dependencies of OpenMP, but it allows you to express more precisely what memory is, or what the dependency is, but also what memory is used when you're using multiple address spaces. That maybe is less likely to get into OpenMP, but it's important for us. And then nesting of tasks is very important to allow things to go on concurrently and control the amount of work that's sort of instantiated at one point. And the picture sort of illustrates how you've got two tasks and then nesting inside, and if you're not careful, you can't even instantiate the work inside the second task before the first one is done. So I'll give a quick example of what we call weak dependencies here. So there's maybe the code is a bit more complicated than it could be, but you've got an outer task with a couple of dependencies and a for loop generating some tasks inside. Because these outer dependencies are ins and in-outs, you cannot enter the outer task until this data is satisfied, which means you can't even start instantiating the work until the data is ready. And that's kind of a shame, right? So the weak dependence is a feature in OMPS 2 that says that you need, subtasks need the data. So the satisfiability information has to be linked in some way from the outer dependency domain into the inner one. But the task itself, the AXP, doesn't use the data, so it can start instantiating the tasks right away. And basically that allows these blue and orange arrows to connect the data directly from their sources into the tasks, the subtasks, and the same without. Okay. So that's just a quick thing on dependencies. Regarding the integration between OMPS and MPI, the typical way of writing, say, OpenMP plus MPI is you have the MPI calls just in the main thread, and then you have a parallel region working with it. And the issue with this is that you end up with quite a bit of time sequential, because the MPI calls and the communication, but also the unpacking and the packing and the unpacking is all sequential, and this can become an issue. So we proposed a new threading level for MPI task multiple, and interaction with the runtime that allows you to do, well, non-blocking, but also blocking calls inside tasks. If you do this without something like TAMPI, there's a risk of deadlock, of course, because of the finite number of cores that you have executing the tasks. So this is important because this allows essentially the whole MPI plus OMPS program to have more of a data flow execution across all of the nodes, because as soon as the data is ready, the task on the recipient node can continue going, overlapping the sort of breaking the bulks here at the BSP model. I'll talk also about dynamic load balancing. So we have a DLB framework at BSC that allows load balancing between different processes on the same node. So this is another example where you don't want to be specific about resources, because if the number of threads is changing, it doesn't make sense to use OMP get num threads or get thread num and use private data and so on, because you want that. This is another reason why you want this to be controlled by the runtime system. And in terms of the integration with OpenMP, I guess you could say an unfortunate aspect of OpenMP standard is that within a parallel region, the number of threads is fixed. So BSC is making a proposal of free agent threads that allow these extra threads, or some of the threads, to join a parallel region and execute tasks, even though, well, not join, I mean, they're not part of the parallel region, but they can execute tasks. So OMPS does this naturally, and we have an OpenMP proposal to do this in OpenMP. So a quick example on load balancing, well, at this point it's on multi-dependencies for the assembly part of BSC's multi-physics code. It's a finite element code. And the assembly, you run through elements, some of them use the same node, so you need atomics, which are expensive. There's a coloring way to make sure that none of them basically of the same color will interact or will access the same node. This helps by removing the atomics, but it ruins the spatial locality. So using the commutative with multi-dependencies, you can break the domain down into tasks. Commutative expresses the fact that they can go in either order but not at the same time, and the multi-dependencies are a way to give a sort of iterator of dependencies because they don't always have the same number of dependencies. If you look at the results quickly, here we have execution time, so down is good, all on 32 nodes, but you have a choice often. This is one of these things where you tune the number of MPI processes versus the number of threads. If you go from the blue with coloring, red, without coloring, red with coloring is a bit better. Multi-dependence is much better than that. The dashed lines bring in the dynamic load balancing. And you can see actually at the end of the day, the bottom orange dashed line is almost flat, which is actually a good thing because it shows that it's no longer necessary to tune this parameter, right? A little bit necessary, but much less necessary than before. And also overall you get better performance because of load balancing with over MPI. So I said at the beginning, heterogeneity is important. This is just an example showing that we even support FPGAs in addition to, of course, GPUs and SMP. And the idea is the application structure should be more or less, or will be more or less, will be the same, but the details of the kernels, the implementation of the kernels, of course, will be different. And in fact, you can have multiple implementations of the same task, and the runtime system can keep an FPGA busy and 2 GPUs busy and all the cores busy by putting the right task on the right device. So here is example with FPGAs. We also have an implementation that runs on distributed memory using MPI communication below. Again, uses mechanisms to control the data transfers. So everything I've said was spoken about so far is for OMPs. Remember at the beginning we have StarSS is the umbrella, OMPs is the OpenMP-like variant, comps and PyComps are sort of coarser granularity. In terms of PyComps, it uses Python, and then the tasks are shown using Python decorators instead of annotations, but it essentially works in the same way. Sequential looking program runs these tasks here in parallel, barriers and so on, and a shared memory illusion. This can run on multiple different platforms. For instance, it can run on clouds, taking advantage of the elasticity that is natural in clouds. Also on Slurm, supports containers, and communication now is not through shared memory, but through files or object serialization. So that was a very quick run through. I've actually been quicker than I thought of what's going
You're
on.
perfectly on time.
What's going on with OMPs, and this is more or less summarizing what I said at the beginning. The difficulty coming from the divergence between mental model and behavior. You need to do the performance analysis. To avoid having super complex programs that are dependent on the architecture, we use tasking as a stable interface, and this allows better maintainability, performance portability, malleability, and standardization through OpenMP is essentially one of the outputs of our work to allow it to be used in practice. And that's it.
Thank you, Paul.
Yeah, thank you. Pascal, you want me to take over for the discussion part?
Yes, please do. I'm trying to share my own screen.
So perhaps until we get the first question, perhaps I can kick off with one question I had in mind, having listening to your exposés. So this idea of task-based programming and separating the functionality of the application from the resource management part, it seems so obvious. So my first question would be, why has this idea not already taken up much more?
Maybe I could.
Yeah, please,
Paul,
perhaps you.
So, I mean, as Olivia said, the idea came out fairly early-ish in the mid-90s, and it has been some time. It's been 15 years, I guess, since it was introduced to. No, maybe I'm wrong actually, but it's been some time since it's been in OpenMP. But as you could see from our presentations, it's not just the idea. I think the details. There are lots of things that need to be implemented to make it work well, and that's why there's a kind of ongoing community of research to narrow the gap between the performance that you can get by hand tuning and so on from the performance that the system can achieve through through a kind of stable and abstract interface. I'm not sure if that helped actually. I don't know, maybe Olivier has
Yes, I agree. What I think is that if you want to embrace these ideas in your application, you have to relinquish part of the control you have on your application. You have to delegate the effort of driving the application to some third-party software, and this may be more or less difficult to accept in the beginning. It was the same some decades ago when people were developing in assembly or very low language level. It was not immediately accepted that structural programming was better, but several decades afterward, we have no compilers that are able to take advantage of the structural programming to have hundreds of optimizing phases in the compiling process. So, but this was possible because the compiler is able to understand what the application is doing, and to do that, the compiler needs to have an idea of the structure of the application. And so this is why we need that with tasks, but we need to convince people that they have to trust us for that.
Thank you very much. And this is perhaps a good introduction for the first question I see here from Matteo Mascagni. He's asking what are the open problems to be solved in this field? So perhaps this relates to what you just said, that a lot of research is going on. So what is still missing to get it shared more widely or used more widely? Who wants to start? I don't feel you're confident on this question.
So I was going to say a few of the things that are, but then when you said to be used more widely, it sort of tripped me. That's what I was sort of thinking. But
then Paul, then take it as two separate questions. So the question of Matteo was, Remy, what are the open problems to be solved in this field? So let's stick to his question first. Sorry.
So I think malleability is a very important one. I think this is not just in this field, but also in general in HPC. By malleability, in case it wasn't clear, I mean applications that can change their resources over their execution time. So this is wider than just tasking. It also involves the resource schedule, the resource management, and so on. But I think tasking can bring something to this this problem. So I think this is a really important one. Both of us spoke about distributed memory support, and I think this is still at a early stage, but I think there's a lot that can be done there. This is actually why I'm working, so maybe I'm a little bit biased on this. And then new architectures, for instance, there's a plethora of new architectures that bring all sorts of issues, maybe even very new things like processing in memory and so on. So keeping up to date on what's being done in the architecture, I think this is another important research direction. I probably forgot some obvious ones, maybe.
But maybe it's an opportunity also, because since there are all these new architectures that are coming, doing the effort of porting every new existing application on this new platform makes a lot of redundant work. So if we can do the effort in some runtime system that are shared among multiple applications, then we can share the work of managing this new hardware, new computing units. So this is an opportunity for the community, I think.
Mm-hmm. And to drive adoption, right? Because it's a reason, really strong reason to use these models.
Thank you. So I see we have here another question from Matteo, and he's asking, what are the most important open problems in HPC applications and how co-design can help on it?
So I must say, if this is an application problem, I'm not really the right person to ask.
Maybe what can, the observation that I have is that many HPC applications are still very bulk synchronous parallelism oriented for now. This was the dominant model for a long time in parallelism. So you have sequences of computation and then of communications, and this was okay while we had uniform processing unit. Even multi-cores were slightly okay, but now that you can have CPU, GPU, FPGA, and all, it's not really possible to have all these computing units finish at the same time doing a computation and then exchange data and then compute again. So application need to evolve away from that, but this need some work in redesigning and redeveloping some existing code. So the problem, I think, is there.
So basically this will require to completely redesign the applications, to reconceive the applications from the scratch. Is that a little bit what you say?
This is sometimes presented like that, but actually applications are always being redeveloped, at least part by part. So the idea is to do that in a more structural way, so that then we can transfer the effort of optimization to tools instead of still having developers to do that. So.
Okay. So now the questions are coming in. I'm sorry, I'm trying to speed up on this a little bit. So Paul, you gave an example of ALIA using task-based programming. Here's a question from Jean-Pierre Panzirac. Can you give examples of HPC applications using these techniques?
So maybe Olivia is quicker off the mark than I am. I know that we're working in a number of projects.
Yeah, we have some collaboration with Airbus in particular, and Ariane, so you know the rockets. So there are several codes that they are developing and that are using StarPU for that.
Thank you. Will StarPU optimize MPI communication, defining communicators, etc.? This is a question from Ralph.
Yeah, so completely. Once you use the distributed execution model of StarPU, StarPU hides completely the use of MPI. So I presented this task graph, and you know the edges in the graph, and StarPU will replace one edge by some MPI I send and MPI I receive automatically. So you can give your existing application and just running an MPI without any any MPI details to work on.
Okay, merci. And the next question is perhaps a little bit for Paul more. It comes from Jean-Philippe Nominé, and he's asking whether you could elaborate a little bit more on standardization efforts that are ongoing or should be done to push good R&D more into mainstream and widespread, what he calls sustainable and solutions.
So I guess this is a question beyond just OpenMP, right? It's a question about in general and where else.
I think it's a question in general, but perhaps with your experience in OpenMP, you can report a little bit on your experience.
So I understand it's
or kind of lessons learned from your effort. Let me put it like this.
So I'm not one of the people that's directly involved in OpenMP standardization, so I guess you'll have to take what I say with a bit of a grain of salt, because I'm not sure. But I understand that it takes a significant commitment to join the standardization bodies, many calls and so on, to get the trust, and then it's not a simple matter of just proposing something and expecting it to appear in the document, right? So you really have to engage with the other points of view. And I mentioned reference implementation, so maybe the reference implementation, we have OMPS and of course the Nanos runtime system and the Mercurium toolchain as part of the OpenMP standardization. Some of the more mature things, like the free agents, for instance, I mentioned, have to be implemented in LLVM so that it can use the infrastructure used within the project. So I guess I'm not really sure what to say, but I think it takes a real commitment to do this. But having said that, I do believe, at least in this context, that it's a very important way to get things, and it links to the other question about driving adoption, right? In fact, that's what it said on my slide, right? I think it's really an uphill struggle trying to get an application to use OMPS, for instance, right? Because even though we've been working on it for a long time, we're not a software development, production quality, and so on across many systems. I think it's super important, and there are many other areas, maybe MPI as well, standardization, where ideas. In fact, I see this as one of the strong ways in general for the research output to be picked up. That doesn't mean that we only concentrate on the things that are close to the standard, right? So OMPS has much more speculative things. The work on the StarPU also is, is super valuable, and the other stuff in the ecosystem. So I guess it's a balance of the two.
Thank you. So we have one last technical question from Bucket I would like to share with you. She's asking, what are the prerequirements in terms of hardware, software, and compiler to install the models of StarPU and OMPS to a cluster?
So it's not, from the point of view of OMPS, it's not much. If you go to the Git repository, there's a few things. You need boost, you need HW lock, you need something, but they're very standard things, and it's very easy to install.
Yeah, it's the same for StarPU, and it is already deployed on some supercomputer in France. So yeah, it's just basic.
And somebody who wants to try this can find also some first tutorials, some step, and some support on these web pages.
Yeah.
Yes.
Well, I think this, Pascal, so it's 12 sharp. I think this is
we are exactly on time.
To close the discussion and to close this Q&A session.
Yeah, Okay, well, thank you very much. Thank you to our audience. Thank you for being here and for your questions. A big thank you to Olivier and Paul for sharing their experience and explaining more in details how they built this white paper. So you will receive the link to the recording if you want to listen to it again. Also, all of our webinars are recorded and they are on our YouTube channel. So if you're interested, do go to our YouTube channel. And I wanted to highlight that our next webinar will be on the 29th of April, and it will be again on an ETP4HPC white paper, but on a completely different topic, HPC for urgent decision making. It's a white paper that's already published, so you can go to our website and check it if you're interested. So thank you, everyone. Thank you, Maike, also for moderating the questions, and hope to talk to you again in April. Bye-bye.
Thank you. Bye.
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 Bye.